Hi, my name is Lance Zurich, and I'm the product manager for the Fischertechnik division at Studica. And today I'd like to share some information with you on the importance of project-based learning for an effective STEM education program. And in particular, I'd like to tell you about the Fischertechnik STEM Lab program. Now, this is a standards-based curriculum program involving inquiry, design, and problem solving that was especially created by noted educator and STEM expert Tom White. Now, the following presentation is largely based on a workshop which Tom conducted at the ACTE Career Tech Vision Conference in Atlanta, Georgia in November of 2012. Now, first off, what is Fischertechnik? Now, unlike a lot of other construction systems that are available that are involved on basically designed around a stacking method of construction, Fischertechnik is a flexible and innovative construction system that differs because it's unique, as the core component allows attachment from all 6 sides. It was designed with an engineering mindset. Because of this, Fischertechnik is used by middle schools, high schools, colleges, and universities around the globe to explore STEM-related concepts, things like robotics, renewable energies, mechanics, pneumatics, and so on. Now, it's also been used by numerous companies, including Porsche, Daimler, Chrysler, and BMW, to name but a few, for industrial simulation and training purposes. A way to learn. Now, the picture here that you see is from a project that Tom White was asked to help out on last year, called The Science of Golf, and it was used in an exposition sponsored by Chevron. Now, the purpose of this exposition was to find ways to get students more involved with STEM education. And as Tom pointed out in his original presentation, the problem too often with STEM education is that even when there's funding in place, teachers and administrators aren't always exactly sure how to go about actually teaching STEM. Well, one of the ways that Tom suggests is by creating exercises like the one pictured, and in this case, what students were doing was they were performing various tests on a golf ball in a wind tunnel. And what, of course, would happen was certain results would occur, but then the students had to discover why they occurred. Now, the way they found the answers to these questions was through the use of hands-on, project-based learning. Now, Tom White was inspired in his creation of the curriculum for the Fischertechnik STEM Labs by 2 famous people, one of which you'll see pictured here, Ben Franklin. We'll look at Ben Franklin's quote that Tom has: "How many mills are built and machines constructed at great and fruitless expense, which a little knowledge in the principles of mechanics would have prevented." The other person was Sir Philip Magnus, who also has a quote here: "The contrast between the listless and often inattentive attitude of children occupied with some ordinary class lesson and the eager eyes and nimble fingers of the same children at the modeling bench is most instructive." Now, what Tom took from these esteemed gentlemen was the need to tie science and mathematics together, as well as the need to provide an avenue for students to engage in the educational process, which results in real learning, as opposed to the way we've always done it approach of lectures and standardized testing. Now, the purpose of STEM education. STEM education needs to provide 3 primary things, capital if you want to, for our society. And that's according not only to Tom White, that's according to the bipartisan Congressional STEM Education Caucus, which is currently chaired by Dan Lipinski and Roscoe Bartlett. Now, these 3 things are, first off, scientists and engineers who will continue the research and development that is central to the economic growth of our country. Now, this is research and development that will ensure that we maintain our place as a country in the world order. Now, you've heard it a lot of times before, and it isn't an exaggeration. This isn't just an educational concern. It's a national security issue. We really have to decide, do we want to be dependent on getting our technology from other countries, or will we create and control it ourselves? Essentially, it comes down to, will we lead or will we follow? STEM education is also important for creating technologically proficient workers who are capable of dealing with the demands of a science-based, high-technology workforce, which, of course, that's what workers are going to want to be part of, because think about it. Today's high-paying, high-wage jobs are technology-centered, and it's only going to be more so as we move ahead. Thirdly, STEM education is important for creating technically literate citizens who can approach the important decisions of today and tomorrow with an understanding of the world we live in. Falling into the gap. According to an article which appeared in U.S. News & World Report on September 21, 2012, entitled "The State of STEM and Jobs," The STEM problem in the United States is most clear when viewed against the gap we see between our high school students and those in China, South Korea, and much of Europe, or the huge volume of mid-level engineers being produced by a place like India. See, the thing is, there's a lot of change going on right now. For example, infrastructure needs have changed. If we look at some pictures of China, China is going to build the equivalent of the U.S. infrastructure over the next 20 years. In India, they're going to do it over the next 22 years. If you take a look at a place like Dubai, not so long ago, just a little over 40 years ago, the tallest building in Dubai was 3 stories. But as you see from these pictures, which are a little more current, things have changed quite a bit. Industry has changed. Now, here's another quote from the previously mentioned U.S. News and World Report article. The sweep of industries affected by the STEM skills shortage was revealing. From healthcare, energy production and distribution, and autos to the whole slowly renewing domestic manufacturing area, transportation, and agriculture. There are no more jobs that require a strong back, said Tom Luce, the force behind the successful National Math and Science Initiative. We have to explain to parents and kids that 30 years ago, you could have a living wage job and not be STEM capable. Today, that's not possible. And as you look at the pictures here, 100 years ago, industry was based on perhaps the assembly line. Someone does a small activity and it moves on to the next person who does another little tweak or another little activity, and then it moves on to the next person. Road activities were replayed over and over again during the day. Things that were simple to learn, simple to do, repetitive, repetitive, repetitive. These days, though, it's less about doing the same activity over and over again as opposed to having to solve new problems every day and having to do a lot more problem solving and a lot more envisioning of new solutions. Once again, there are no more jobs that require a strong back. We have to explain to parents and kids that 30 years ago you could have a living wage job and not be STEM capable. Today that is impossible. Now, here's another quote from the same U.S. News and World Report article. When somebody asks, well, is STEM really necessary for me? I mean, maybe I don't want to become an engineer. Well, STEM is not really about the rocket scientists, although a few more would never hurt. It's really about the middle class. It's less about the folks who would design the airplanes than the ones who would build them. The guys who used to pour the steel now have to know how to program and instruct a robot to do it. Of course, while all these things are changing, technology has changed. 50 years ago, computers filled a room. Today, almost everyone has a smartphone or another handheld device that exceeds the capabilities, the speed, the memory, the storage of anything we might have previously imagined. While this is going on, we have a skills gap that's developing. Now, these are just some of the areas that our students and our future workforce will need not only to compete on a personal level, but also for us to, as a country, to compete on the world stage. They're going to need to have these skills. They're going to need to have the ability to do measurements, to do analysis and signal processing, to do presentations, decision making, to know about data logging, control systems. Because we're going to need things like sustainable designs. We're going to need cost-effective use of materials and infrastructure and process control. So these are the things that our students, our future workers, are going to need to be proficient in. Meanwhile, how about those students? The next generation. This map over here shows the average freshman graduation rates based on state, and this was based on a survey they did in 2008-2009. And these are the projected graduation rates of these freshman students. Now, the problem, as Tom White pointed out in his original presentation, is due to the way that this map was devised. For example, they would students that they may have talked to said they were going to drop out of school, but who claimed that they were going to pursue a GED eventually, they were counted as being potential graduates, even though that's probably not the case. So with that in mind, the rates that are listed here are actually quite generous. But in truth, it's fair to say that a good 30% of our current student population is underperforming. Meanwhile, right at this moment, 3 million job openings in the United States remain unfilled. But at the same time, our unemployment rate is hovering near 8%. And that's primarily because the workers who are available, who could possibly fill those positions, can't, because they just don't have the background, they don't have the knowledge, and they don't have the qualifications to do so. Now, while all this is happening, the big question is, How has education changed? Well, 100 years ago, students were arranged in nice orderly rows. They listened to lectures given by a teacher who might share an example on a blackboard, and they took tests to see how much they had retained. And today, in many modern public schools, students still follow the same passive model of sitting in rows. They listen to lectures. They take standardized tests. Sure, you might have a few computers around. You might have a computer lab, but really, not much has changed. Now, here's some food for thought. If you look over here at the top, this is an example of how one student answered a common geometry question. Find x. Oh, they circled it. There it is. Here it is. And, well, too often, the problem here is that students encounter things in schools that just seem too abstract to ever to be useful in their lives. No one has helped them to make the connections, so what happens? They ask the same 3 questions over and over again. Why do I need to know this? Where am I ever going to use this? What do I have to do to get an A? And can you blame them? Now, the current educational system. Well, essentially, the current educational system is based upon the model created way back in 1907 with the help of the Carnegie Foundation. Now, back then, students were deemed as fit for college based on certain requirements they had met. For example, at that time, they decided how many years of math a student would need or how many years of reading, things of that nature. But this was all based on the needs of that society, the society of 1907, back then. But keep in mind, back then, students would go to work in factories where they needed not to ask questions, and they didn't need to solve problems. They just needed to know how to follow directions. But here it is over 100 years later, and our needs are almost the opposite. Because right now, we need students who can ask questions, and we need students who can solve problems. This brings us to the Fischertechnik STEM Lab program. Now, this is project-based learning that's focused on standards of today. Now, when Tom White put together the Fischertechnik STEM Lab program, he had several goals in mind. First was based upon his observation that various types of teachers have different strong points. For example, when Tom thinks about himself, he's obviously really strong in creating curriculum, probably much stronger than he sees himself as being, let's say, a regular classroom teacher. But, of course, everyone's different. But with this in mind, Tom focused on creating a curriculum that would provide a broad foundation of tools for all types of teachers so that they could be successful in providing this class, and so that they could instead focus on the needs of the students. Essentially, what he wanted to give them was a turnkey solution that would provide everything they would need in one place. And of course, provide teachers with curriculum that promotes STEM learning and integration through extensive use of projects and problems. Now, the goal was also to enable teachers to provide students with engaging curriculum-based projects that had an authentic objective in solving real-world problems, and which contained embedded academics. Now, the Common Core standards addressed in this curriculum are the current standards in place. Keep in mind, reading no longer means just reading and understanding literature. It also refers to being able to read technical documents. Same token, meeting the current writing standards now also means a student should be able to write technical documents, and so on. Now, once again, referring to the same article from U.S. News & World Report discussing the state of STEM and jobs, there was a summary that was provided of the results from 3 days of workshops and discussions at the first National STEM Education Conference in Dallas, Texas. Now, this brought together some 1,600 people from hundreds of different organizations, but didn't matter where they came from. One of the major conclusions that they pretty much all agreed on was that hands-on learning that links math and science to the real world works best for all students. Now, also, I have to add here, Tom White built this curriculum around Fischertechnik because he truly believes that Fischertechnik is the ideal construction set for an engineering-based curriculum program like this. Now, keep in mind the materials can be used and reused. Things that are built can be taken apart and reassembled into something completely different. And it's much more economical than purchasing an expensive piece of equipment that might be used for 1 or 2 experiments or projects. Like actually a lot of STEM education solutions that we see out there currently that may cost thousands of dollars, be used once or twice, and then put on a shelf until next semester's class. So the nice thing is it goes without saying this is economical, plus it also offers limitless creative opportunities. Now, what students are going to experience? Under the project focus model, students are told up front what they need to learn and understand, and they are provided with different tools and pathways to achieve this goal. Now, among other things, students must learn the documentation process. They're going to create a design brief, keep a digital engineering journal. They're going to do research outside of class. They're going to do homework as well. So they're going to have that, they're going to acquire knowledge through inquiry and exploratory research. They're going to learn technical literacy by the task that they're given. They're going to learn how to collect data. They're going to learn firsthand how data acquisition works, how to process data, how to put the data into graphs and other formats, and so on. They're going to acquire necessary science, mathematics, and technical skills through carefully designed enabling activities. They're going to create prototypes of their solutions using the advanced fischertechnik modeling system. They're going to create programming solutions to control their prototypes that they've created, and then they're going to create the final documentation for the entire project and present the findings. Now let's look at the way one of these, the curriculum is laid out. If we look at the high school mechatronics project themes, they're listed over here, and I'll just go through them quickly. The high school mechatronics curriculum covers sketching and documentation, and this includes documenting the whole process, the trial, the error, every bit of it. It also includes learning about structures, for example, learning about the basics of different types of structures and testing various designs, such as in this curriculum they're going to learn about the structures of different roller coasters and learn about the physics involved and things like this. Mechanical systems, for example, how do gears work? They're going to get into electronic systems, learn how circuits work, how things are wired, and so on. Control systems, how are they used? Sensors, what do they do? How are they used? Etc. And they're going to go on until they get into the fundamentals of robotics and automation. If we look at the other lab, the middle school project themes, pretty much you'll see that they kind of mirror what was covered in the high school version, but it offers a more basic version of the same themes, essentially with the emphasis on here more on providing the basic groundwork needed to be an informed and literate citizen in our modern technology-based society. But of course, there's some other things that won't be covered in the high school lab, so it's a good basis to have. Now, let's look at the curriculum structure. In both cases, what you'll see is that each unit in either the middle school or the STEM lab or the high school STEM labs is laid out in this order. There's a purpose, there are concepts, there are student deliverables, assessment and evaluation is included, an outline, standards, an authentic project scenario, a daily teaching plan, supporting activities, and resources. Now at this point, what would probably be most useful is to show you actually what the curriculum looks like. So let me just break out of this PowerPoint here. Bear with me a second while the screen goes black for a second. I promise we'll come back. And here you see, this is what you will find if you open up your, if you put your high school STEM lab curriculum disk in your computer. This is the first screen you will see. And what you have over here, as you see, it contains both the teacher and student version. This is the curriculum itself, as well as the ROBO Pro software, which is used to program the various fischertechnik robotic models. Now, the student version of the program here is essentially the same as the teacher's version of the curriculum. It's just minus the standards related material, the rubrics, and other instructor related information. Now, let's open the teacher version. And let me move this over to share with you here. Okay. As you'll see here, if we look at the high school STEM lab program, we have the sketching and all the things that I talked about before in the themes, the sketching and documentation, mechanical systems, structures, introduction to electricity, etc. Let's take a sample unit, and once again, let's just see how that curriculum is laid out. So we'll look at introduction to programming here. And if we click on the first page, this is this picture here that you see at the top, I should mention, is a graphic representation of the ROBO Pro software. Now, as you'll see, it's designed to use icons that represent the different actions, which you arrange in a flowchart-like manner to create the program for your robot. Now, ROBO Pro is great because it allows students who may not have any prior experience with programming of this sort to quickly become comfortable with doing so. Now, as we scroll down here just a little bit, the first thing we'll see under programming is the purpose of the project. This is, of course, the whole section spells out the purpose of the project. Why are we doing this? And as well as what it is that we hope to accomplish here, what we hope the students to accomplish here. Then we get into concepts, which basically outlines all the concepts that are going to be addressed and really points out the big things that you will need to learn as a student from this project that will be useful and vital to understand and know. Not just today, not just to get through this project, but 10 years from now. These are the things that you want to bring with you that are spelled out here. We go into an outline. Here we spelled out exactly what is covered in the project. So we're going over the things we're going to be visiting. We're going to be touching upon flow charts, word problems, state machines, open loop systems, closed loop systems, flow charts, etc., PLCs. We go down a little bit, and this is what's going to be really important to the teachers, of course, are the standards. Here we address, this is where we address the specific standards that are going to be met by this particular project section and spelled out. This is, of course, the educational justification for the whole project itself. Here we have the Common Core math standards. They're all spelled out there. You'll see there's things like creating equations, interpreting functions, linear, quadratic, and exponential models, modeling with geometry, etc. So this is much more than just, science and robotics. We're getting into math. We're getting into the reading standards for literacy and history and social studies. We're getting into the writing standards for literacy and history, social studies, science, and technical subjects. Of course, we're hitting on the science standards. We're hitting on the standards for technological literacy. We're hitting on the ISTE created standards. So once again, it's very comprehensive. You've got a lot of different areas of standards, and this is going to be for each of the units, for each of the projects in both the middle school and the high school sections, curriculum setups. Now, as we go down here, then we have the assessment. Of course, this is where it spells out how the student performance is going to be assessed. For example, looking at the general rubrics for literacy here, some of the things that might be spelled out, for example, looking at the students, how well they deal with the main idea. Not yet would be attempting to create a main idea, but lacks focus and clarity. No mention of argument other than their own. They're getting there if they create an argument that makes note of claims of other than their own, meets expectations when they create a convincing argument, develops and presents argument and counter-argument fairly, or exceeds expectations when they create a convincing and meaningful argument, develops and presents argument with counter-arguments fairly and fully. That's just one example, and of course, these rubrics are included in each of the sections. Underneath that, we get into the essential question. Of course, this is the big idea. Why is this important? Now, how well students answer this question is how we see as educators whether they understand all the pieces. Next, we get into the student scenario. The student scenario right here. Now, this is the real-world scenario the student is given an answer to. Where will I ever use this? In this case, the student is given the scenario that they are a controller programmer working for the Simplicity by Design programming company, and that their company specializes in designing elevators. So they have a task that's related to designing elevators. Now, underneath that, you have the daily plan. And this is where we go day by day. This is an outline that acts as a guideline, a roadmap, so to speak, spells out specifically what we are looking at today and what we want to accomplish today. And as you'll see, each day's activity provides a building block towards the big project that students are going to be required to complete at the very end. And each day will include links to all the different areas they need to address. Like, for example, on day one, if they need to address starting an engineering notebook, they're going to be able to click to a link that explains how an engineering notebook is put together. If they need to address doing a design brief, there's a link to putting together a design brief and so on. Or if they need to install the software, there's going to be a link to show them how they can install ROBO Pro software. And this is, of course, useful not only for the students, but also for the teachers as well. All of the material is right there for them. Moving right along, as you'll see, they're given different tasks. For example, on day 7, they're given a question to address. How does my dishwasher know when the dishes are clean? Well, of course, a dishwasher just doesn't know if the dishes are clean. A dishwasher is programmed to do certain things for so long, and that's something you're going to address there. There's another section in here where they're going to, students are going to have to basically discuss how the controls on an elevator work. For example, how come if 2 people on different floors press a button at the same time, the elevator always goes to one floor instead of the other first? Now, some of the other things covered in this section, for example, include how data is taken from a sensor and recorded, or taking files from that ROBO Pro software into Excel to be worked on and then being able to put them back again, working on robotic positioning, things like this. Once again, each unit builds on the one before, and each unit is subsequently more complex. Now, at the end of all of this, there's a big open-ended project where students must combine all the things they've learned and worked with in the units before. And this really helps to reinforce and tie together for students what this is all about. Now, on top of that, as you'll see, besides all the days of activities here, and in this case, we're going up to 35 days of activity in this one unit, you have vocabulary, you have resources here. And in fact, these are all web-based resources that were carefully selected. And one of the things we have to point out is during the course of the lab, students are going to be required to do a lot of background research and reading as well, as we mentioned before. And as a lot of this is internet-based, one of the things that we're going to teach students, that students are going to learn by doing this, is they're going to learn how to find good information on the internet and how to be able to tell the difference between good information and bad information so they can make the proper judgments. Now, of course, and also at the bottom here, you'll see all various Word documents are included. Once again, you have PDFs and PowerPoints and things. And you've got all the material on, for example, once again, there's a document on writing the design briefs, or there's, what have you. There's the rubrics are here as well. Now, there are also links to access all the actual fischertechnik instruction manuals, and these are the manuals that are normally included in all of the box sets, the sets that are commercially available. And the reason for this is throughout the course of the curriculum, students are going to be asked to build various models from these manuals. Sometimes they're going to have to create the whole model to learn something about how the system works, and sometimes it's only a small section so they can learn how a little subassembly is built. But either way, they're going to be able to access all of the materials from, once again, these fischertechnik manuals, which are all going to be included in here. Now, of course, the ROBO Pro software, as I mentioned, is included, and also includes sample files for various models that are going to be addressed. There's also, as we discussed before, a lot of detailed information not only on installing the ROBO Pro software, but also, in case this comes up, how to configure your ROBO TX Controller, and so on. So basically, what you have here is that's just for this one section. And once again, this is just one page that we've gone through on the section of programming. There are, of course, different things in here. You get into the introduction to ROBO Pro software. You get the introduction to the TX controller, the flow charts, learning about open loop programming, learning about closed loop programming, digital branching, edge triggered versus level triggered, combinational logic, programming with variables, subprograms, and so on. And once again, these things will apply, the way that the curriculum is laid out, that would apply to if we go into the mechanical systems section. Once again, you're given an introduction. You're given the concepts, the outline, the standards are addressed, the reading standards, the writing standards, etc. And of course, you're given the assessment, the essential question, the student scenario, and the daily plan. And that's for all of these areas here. And once again, while this is just, we're of course looking at the high school version here, but this is also going to pertain to the middle school version as well. All this is going to be spelled out, all the standards, all the assessments, all the day-by-day activities, the daily plans are going to be there. That's all going to be there. The reference materials will be there, etc. Now, going back to our PowerPoint here, we'll bring that back. Just a second. Okay. Each STEM Lab kit is packed in its own plastic sorting box for organized storage. And I should also point out, each set includes the complete curriculum disc, like the high school disc that we just looked through. It includes the ROBO TX controller, which you'll need, of course, for programming, the ROBO Pro software, and all the required parts. So everything you need is in that one box. Now, which of course brings up the question, well, how many sets do I need? Well, per Tom White, he recommends ideally one kit per 2 students for the middle school STEM lab. Now, the reason for this is that 1 kit per 2 students will keep each student engaged and involved in the activity, as opposed to if you had more students involved, you'd have essentially 2 students really doing the work and others just observing. Now, when you get into the high school section that we just went through, due to the more involved nature of the projects that are being addressed, you can get away with having 3 or even 4 students per set. Still, ideally, the smaller the group of students per set, the better. Now, using this in keeping this in mind, let's take the average classroom of 20 students, let's say. For them, you would use anywhere from, let's say, 5 to 10 of the STEM lab sets, depending on the section, whether you're covering the middle school or the high school section, and the budget you're working with. Again, you essentially want to aim for 2 students per set. Also, keep in mind that what you have here when you look through all the days of activities is that essentially the middle school STEM lab set is set up to provide 6 months worth of activities, 6 months worth of classroom activities. Let's assume that you're conducting a class a day, a 50-minute class a day in STEM education, or an hour class a day in STEM education. Essentially 6 months of materials are included there. With the high school set, it's actually closer to a year's worth of material. Now, with that all said, we want to thank you for taking the time to view this presentation. Well, hopefully we've got you interested, and hopefully you'd like to get more information on this program, request a quote, or speak with one of our dedicated educational representatives. If so, you can call us at Studica. Our number, of course, 888-561-7521. You can also visit the fischertechnik STEM Lab page on our website, which, of course, is www.studica.com/fischertechnik-STEM-lab-program. Or if you prefer, you can just email us at stemlab@studica.com. So on that note, once again, we thank you for your time and your interest, and we look forward to talking to you soon.